Hi, I'm Michael,
And I'm Rish.
and today we're going to be teaching about Kepler's first law.
Yay!
So, Kepler first created his laws in 1609. He did this following his tutorship under some old guy astronomer, also commonly known as Tycho Brahe. Now, this old guy was a very well known and established astronomer back in the day. However, he did not believe in the theory of heliocentrism. He believed that the sun revolved around the Earth. And so, in order to ensure that his student, Kepler, would not be able to prove Copernicus' theory that heliocentrism is correct, he actually withheld most of his research from Kepler. Like, wow. But fortunately, Kepler was able to figure out and prove that his theorem was correct. And in fact, Kepler's laws became so well established and important that they eventually led to the creation and had some influence on Newton's laws, which, as we all know, define the laws of motion that we know today. So, what exactly is Kepler's first law? Well, Kepler's first law basically says that the Earth revolves around the Sun in an elliptical orbit. Now, why is that? Well, let's say that this big circle here is the Earth's orbit, with this being the Sun located at the foci, this being the center of the elliptical, and this being the Earth here. Now, the Sun is exhibiting a gravitational pull on the Earth and causing the Earth to travel in this kind of direction here. Now, as the Earth travels in this pattern, it's slowly gaining more and more speed, causing it to start rapidly speed up, and then it's going to slingshot all the way around here, and which is why the distance that you see from the center to here, from the Sun to the Earth, is larger than the distance from here to here. In fact, we actually have names for these positions. When the Earth is closest to the Sun, that's known as the perihelion position. When this Earth is farthest from the Sun, that's called the aphelion position. Now, don't be fooled by how this diagram looks. It's not actually this big of a difference between the distances between the Sun here and the Sun here. But while there is a difference between the distances, it's not actually it's too negligible for us to actually notice any changes in our weather. But it does occur, and Kepler was able to discover that, which is why he was able to figure out that the Earth travels in an elliptical orbit.
Wow! Alright, now for the fun stuff, the physics behind it all. So, as you may know, Kepler's first law states that a planet moves around the Sun in an elliptical orbit with the Sun at its focus. Now, Kepler's law can be proved through two main ideas: conservation of angular momentum and conservation of energy. Now this, as we all know, is the formula for kinetic energy, 1/2mv². This is the gravitational attraction between the Sun and the Earth at different points. Radius, mass of the Sun, mass of the Earth, the universal gravitational constant. This, as everyone may know, is the formula for angular momentum. L is equal to mr² I omega. Now, as the Earth goes this way, the radius decreases, and so, for the total energy to remain the same, the velocity must increase. Okay? So, as we're going this way, the radius as it's approaching its perihelion position, the radius has reached its minimum, and the velocity has reached its maximum. That's how the total energy remains constant. So, if we go further along this derivation, and we eventually go to the magic, aka differential calculus. So, and through this wonderful magic, we get to the definition of an ellipse. Now, everyone recognizes this equation probably, right? X squared over a squared plus y squared over b squared is equal to 1, where a is the length of the semi-major axis, b is the length of the semi-minor axis. Now, what you may not recognize is this equation right down here, where r is equal to p, which is the parameter, which is basically just parameter of the ellipse, over 1 plus e cosine theta. Now, where e is eccentricity of the ellipse, so this is the standard form of an ellipse in polar coordinates, where if you do all this differentiation out through differential calculus, you get something like this. Okay? And e is the eccentricity of the ellipse. Now, eccentricity, that's a weird word, right? Well, it basically means how round the ellipse is. So if e was 0, then it's not odd at all, right? So it's perfectly round, a circle. But as we know, this value is never equal to 0. through observations in astronomy. So the orbit must therefore be elliptical, and thus Kepler's law has been proved.
Wow! Now, Kepler's law has a variety of very cool applications. One of these being finding planets in other solar systems. So, here's us on Earth, and that's our little telescope pointing at a star in another galaxy. Now, we can see the stars because they're obviously very bright. However, the planets, when compared to the star, are very dark and they're extraordinarily difficult to see. However, being as we can see the sun, we can actually determine whether there's a planet rotating around that body. Now, we can do that because of that, again, that elliptical orbit. You see, as the planet goes around the star, it actually acts a force back on the sun, causing the sun to do a little, I guess you'd call a wiggly motion, which is demonstrated here. So the sun is going to move in like a slight circle in response to the planet. So if we can detect that the sun is moving in this little wiggly motion, then we can determine that there is a planet around that star. Yet another application for this principle is satellites moving around the Earth. So let's say you want to shoot up a satellite into the sky. Well, we need to determine its orbit because we don't want it to just simply crash back into the Earth. So if we have a little TIE fighter here and we want it to rotate around the Earth, then we need to ensure that whenever it reaches its perihelion position, where it's closest to the Earth, that it's not so close that it's going to be caught by the Earth's gravity and go into a little death spiral.
Alright guys, now we're going to test what you've learned in our presentation today. So our first question gives you a diagram of the Earth orbiting around the Sun, and it's pointing to this position in the Earth's orbit. So, what is this position called? A. Perihelion. B. Dandelion. C. Aphelion. Or D. Zenith. Alright, so I'll give you 5 seconds. Jeopardy theme song. And okay, so if you guys were thinking perihelion, you would be correct, because this position is when the Earth is closest to the Sun, and so that is the perihelion position. So now, number 2. According to Kepler's first law, the conservation of energy statement can be written as A. The total energy is equal to 1/2 mv squared minus mgh. B. E is equal to 4/3 pi r cubed minus pi r squared. C. E is equal to 1/2 mv squared minus g capital M lowercase m over r. Or D. E is equal to 2/5 mr cubed plus mgh. So I'll give you 10 seconds to remember this one. Okay, so if you were thinking C, then you are correct. Because remember, 1/2 mv squared is the kinetic energy of the Earth as it rotates around the Sun. And Gmm over r is the gravitational attraction between the Sun and the Earth. Okay? So G is the universal gravitational constant. The capital M is the mass of the Sun, which is huge compared to the mass of the Earth. The lowercase m is the mass of the Earth, and the r is the radius in between them. Okay? So, I hope you got both of these right. Well, we hope you enjoyed our video of Kepler's law of planetary motion. Thanks for watching.